Okay, I think everyone's taken their seats now, so we can get started. I had hoped to show off my fancy t-shirt today, but as a few of you have discovered, it is not warm in here. If you're sitting under the air conditioning, I feel sorry for you. I'm getting blasted right here. So I'm going to keep dipping backwards and forwards. So we're here today to talk about load testing. This is something particularly close to my heart. In my day job, I'm interested in performance testing and performance optimization, so we do a lot of load tests. And I've seen a lot of bad load tests, very few good load tests. So hopefully in the next 50 minutes, I can impart some knowledge, some experience that we've come across at Skipjack about what makes a good load test, how you can be successful, and what some of the pitfalls are that you might encounter. This is me. I used to have more hair, clearly. I'm Rob Harrop. You may remember me from the old days. I was involved with the Spring Framework back when that was first starting, but nowadays I'm CEO at Skipjack, and my main focus is on performance. One of the first things I like to think about when we think about load testing is, and any kind of performance optimization, is why bother? We don't want to do something if there's no reason. There are loads of things we can do in software engineering that don't really have a purpose. I know I've procrastinated many times by just aimlessly refactoring code bases, which seems to be something you can do forever and ever and ever. And sometimes it feels like a lot of the things that we do fall into that category. But performance testing and performance optimization is not one of those things. Just last year at the AWS reInvent Summit, the CTO of Trainline got up on stage and said they reduced the latency, I guess, of their pages or of their API calls by 300 milliseconds, and customers spent an extra £8 million that year for 300 milliseconds. So, sorry?
How does he know for sure there is the relation?
How does he know for sure? That's a good question. This is actually a quote by Benjamin Franklin, time is money. But it isn't just Trainline. There are kind of an incredibly large number now, and an increasingly large number now, of case studies where people have shown that increasing performance increases their revenue. But to answer the question that just came up here, how do you know that those are the factors? Well, there was an interesting experiment done by Microsoft. They decided to figure out just how much impact performance had on Bing revenue. So rather than try to make the site faster or do anything fancy, they slowed the site down on purpose for 10% of their users. And they discovered that 100 milliseconds slowdown reduced overall revenue for Bing by 0.6%. Just 100 milliseconds, which on Bing revenue is probably like, I don't know, 100 quid or something. That was cheap. That was cheap. And part of any kind of performance optimization process, getting these 100 millisecond, 200 millisecond, 300 millisecond improvements, is first being able to quantify just how well your system performs, then being able to do some optimization and quantify then how's it perform now, and then compare the differences. Can I detect an actual change? Load testing is then a process. It's not something you just do. You don't just do a load test and then say, okay, well, I've tested the load of my site now and it's all fine and my system's fine. It's a process. And in fact, it's a continuous process. Every time you make a change, every time your audience profile changes, the load on your site changes, you need to keep retesting. In fact, you should be testing your site almost as much for performance as you are for functionality. If you're running every build, some kind of acceptance test, or maybe every night, then you should be doing the same kind of thing for performance, because you have within your code changes, you have the ability to really affect the performance of your site. And if 100 milliseconds is 0.6% revenue for someone like Microsoft, how much is it for your business? I've seen many bad load tests, which is often the root cause of many bad performance optimizations. If you can't test how well your site performs, it's going to be impossible really to optimize it well, because you're not seeing the actual effects of the optimization. There's a process. First, we need to figure out what our purpose is. Why are we doing a load test? Are we doing it because it's a checkbox feature in some kind of requirements documentation? Are we trying to figure out some kind of capacity planning question? Are we trying to run optimization? Each of those things is a slightly different question and requires a slightly different approach. Knowing that, then we can work out a design. We can figure out exactly how we're going to answer the question that we have. And then it's just a case of running it, which is kind of the simple part, although a lot of the effort goes there. Analysing it, which is often the hard part, and none of the effort goes there. And then at some point, there'll be some kind of glory, maybe. Now, I want to focus mostly on how do we design a load test? How do we come up with the purpose? How do we ask the right questions? When we're running it, how do we run it correctly? How do we avoid making mistakes? And then how do we analyze the results? Getting these things right will give you a good quality load test. It's worth spending some time on design because once you've designed a test, you can reuse the design again and again and again. It's not like every test requires a new design. It's like every time you run your JUnit test suite, you have to redesign the test suite, right? You can reuse the design. But some forethought into your test suite does help. So how do we do this? What does it even mean to design a load test? Well, first, I hate the phrase load test. It's not like you have a line of code somewhere that says assert is fast, and then that passes and your site is all fine. It's not a test in the sense that we're all really familiar with tests. It's not a pass-fail kind of thing. It's very much a qualitative kind of thing. You know, there's going to be some fudge factor where that's acceptable, that's not acceptable. But there's also a historical, like an ongoing aspect to this. You want to make sure that your performance isn't getting worse over time. Ideally, it's getting better over time. These are things that are different from a normal JUnit or an acceptance test. So I don't really like the term test. Haven't really got a better phrase though, so it's just a pointless criticism. But don't think about it as being like an assertion style test. It's not a true, false, pass, fail. We're going to start by defining our purpose. We talked a little bit about that, but I want to dig into what that means. And then we need to spend some time constructing a test plan. If anyone's ever used JMeter, JMeter is a perfectly fine tool, great, many of you have, I'm sure. It's a perfectly fine tool for this. Don't let anybody tell you that you can't do good load tests with JMeter. The tool, typically, isn't the limiting factor. I saw some snapshots from this morning's talk, maybe, or yesterday's morning by Kevlin, garbage in, garbage out. That's definitely the case with their load test plans. If all you do is simulate 4 users hitting your homepage repeatedly, don't be surprised if that isn't an accurate representation of how your site performs, because that's probably not how your audience behaves. So what do I mean by purpose? Well, load testing is such an ambiguous term. You often get told by people in the business, or maybe you're a consultant and you're writing a requirement stock, do a load test. But what does that mean? What questions are we trying to answer? Typically, we're trying to answer one of these 3 questions. What latency, what response time do I see with some number of concurrent users? Notice this bit is important. This is not a useful question. What latency do I see? Because without this bit, well, it's a sort of ambiguous question. It doesn't really matter. You can generate any latency you want, really, if you've got 1 user or 100 users. This is important. The X concurrent users is important. You can flip that on its head. How many concurrent users can I handle before the latency exceeds some bound? This is a capacity planning kind of question. You might have some service level that says, hey, you know what, we don't want our page load for our new e-commerce site to be more than 2.5 seconds. So when we're provisioning our new cloud servers, how many concurrent users can I handle before we stop doing that? That's a useful question to ask. And obviously, an all-important question is, how many concurrent users can I handle before my system falls over and dies? That's a question that everyone should know. Because there's nothing worse than being woken up with an alarm from PagerDuty or whatever that says, hey, you know what, you've now got 80% CPU utilization. Okay, but what does that mean? If your system can still handle another 200, 300, 400 concurrent users, maybe there's no need to be woken up by that. Understanding this, understanding your saturation point is a critical thing to be able to do capacity planning and to do proper alerting. Before I dive into how we answer those questions, I want to talk about latency a little bit. Latency is one of the most abused measurements in all of software engineering. If you see a tool that's reporting average latency, throw that tool away. Average latency is useless as a metric. It's useless for mainly 2 reasons. One, An average assumes a nice bell curve like that. You don't get that with latency. You get massive fat tails that go out for ages and ages and ages. Your average latency might be 2 milliseconds, but your 95th percentile might be 40 seconds. That's not unusual. So you need to just ignore the average in that sense. But also average is useless because it conjures up in our mind something that's wrong. We might assume that average latency means average experience of a customer. But it isn't, because customers make multiple page requests, multiple API requests, multiple interactions with the system. And each interaction they make gives them a higher percentage chance of seeing something out into the tail. This is talking about individual request probabilities, these tail latencies. It's not talking about what you as a customer experience. So all you should care about when you're doing latency measurements are the tail percentiles. 90th percentile maybe, 95th, 99th, and 99.9th, almost certainly. These are what matter. Just remember that nearly all of your customers will at some point see latencies worse than 90th percentile, maybe even in the first few page requests. If you're serving up images, you're serving up style sheets, you're serving up API requests to do multiple things, if you've got a chatty system, almost certainly everyone's seeing something worse than this in their first interaction. A great measurement you can take if you don't have the ability to do this is maximum, but it's obviously susceptible to measurement error because you can't correct it downwards. If you see some crazy outlier that you might never ever see anything close to it again, you can't correct it. But for best results, you should be plotting a histogram. The histogram will tell you everything you want to know about your performance. You can even get a histogram now in tools as basic as Google Analytics. So there's no real excuse for not having a full distribution, a full histogram of your data. This is what I did a performance test for to get some data for this presentation against the Skipjack website, and this is what the latter, so the 95th onwards looks like. So I'm guessing this is around about, I don't know, 1.5 seconds maybe, the 99th percentile, but they're way out here. The max is like, I'm so short, like 10 seconds, and then obviously this tail here. But what we'll see, because people make multiple requests on our site, is they have a higher percentage chance of being out here. The average in this case was something like 800 milliseconds. So it's really not a good measure. And that's against a site that's been heavily tuned. The less tuning there is, the more microservices you have, the more network hops you have, the more systems involved with serving an API call or serving a web page, the more variation you'll see in the distribution. This is a super simple site. It serves up some time leaf stuff in Spring. It's like super easy. Anything more complicated than that's going to have a lot more variability. So if we think back to our questions, it's kind of a shame if we have to choose one question and not all the questions. You might want to answer multiple questions at once. And in actual fact, what you should be doing, if we're doing a load test properly, is trying to answer all those questions at the same time by gathering a whole ton of data about your load curve. And what I mean by your load curve is something like this. It's how your system responds, both in terms of throughput and in terms of latency percentiles, as the number of concurrent users increases. Don't just do one load test with 10 concurrent users or 20 concurrent users. Do a series of load tests for a series of ramping up concurrent users, and then you'll start to see how your system responds. And I'll show you later on how to figure out where to test to and where to test from. Now, this is kind of an idealized curve. We might all like to think it's going to be linear, but it's not. We might then like to think it's going to be something like this, where it's going to be like a plateau. Probably won't be that either. What you'll most likely see is it'll come to here, and it'll start to degrade a little bit. And what we're interested in doing is finding this point here before it starts to flatten out and degrade. That we'll call our saturation point. And we'll say that that is the point we can push our system to before things start to get terrible. If anyone knows a little bit about queuing theory, when a system is saturated, the latencies essentially increase infinitely. So you can just keep throwing people at the site. If you don't want to create bad latencies for a test, you can do so by just overloading a system for as long as you want, and it will get as bad as you want it to be. The most important piece of any load test is not the machines you run the test from or the machines you run the test against, it's the plan that you put in there. Because if that's not indicative of your audience, then everything else is irrelevant. You can have a great test rig, you can have an exact copy of production for your load test, doesn't matter. And I don't really like the term plan either, but I have got a better term this time, which is model. The issue with plan is this. Plans are prescriptive and deterministic. They say, hit this endpoint, hit this endpoint, hit this endpoint, stop. Well, unless every user of your system behaves exactly the same way, then that's not at all indicative of what you'll see. And you can get some incredibly strange behaviors in load test if you just keep doing the same thing over and over again, where all the users become interleaved and everything they ever need is in cache all the way through, and it makes your system look really, really fast. And nobody's ever trampling over everybody else. Like in the real system, you don't get any of that. So you need to have a model that is indicative of how real users look. Something that maybe is descriptive of behavior and probabilistic, like your real audience is. So this is what a normal test plan would look like. I've done something for the Skipjack website, which is very simple, but we might get the home page, then the offices page, then the jobs page, then the team page, and we'll cycle back around and we'll do it again. And then maybe we'll run like, I don't know, 100 threads to simulate 100 concurrent users all doing the same thing. That's where load tests go to die. If you're doing that, stop. Stop doing that right now and do something else. Do something where the test plan reflects your actual model. And the way to start is to first start thinking about what user behavior looks like. So let's just assume there's one entry point and everyone hits the home page first. And then we know that 10% of our users go onto the offices page, 30% go onto the team page, 25% go to the jobs page, and 5% will go back to home, and maybe they'll go on again. And notice 10, 40, 65, so 35% of people just don't do anything else at all, which is realistic in many systems as well. You know, a lot of people just get to the first page and do nothing else. This kind of model data you can pull from production, you can pull from your real systems. I pulled this from Google Analytics, roughly approximate to what our audience does. But there's one thing missing. This is fine, like we know the probability that someone will do something. So we capture the fact that each user is different, and the probabilities capture this difference, but people also wait. They don't home page, offices page, team page. I can't navigate a website that fast, and I'm guessing none of you guys can either. People wait, they pause, they stop for a little bit. So I capture these as well. These transitions have a wait time or a holding time. And you can capture this roughly from something like Google Analytics or from your log files. And I keep talking about capturing this data because I want to talk a little bit about that in some detail, because that's the best way to build these plans, is to build them from real data. Now, of course, not only are wait times an actual thing, if your load test model plan doesn't have wait times in, it's wrong. Unless you're doing some kind of incredibly high frequency, high speed, low latency trading system, which is unusual, where there's another system moving as fast as it absolutely can hitting you, chances are API calls have pauses in between them, humans have pauses in between them. And wait times are interesting. They are typically non-zero. It is unusual to find zero wait times. Wait times are drawn from a distribution. They're not fixed values, right? It's not like the wait time going from the home page to the offices page is always 1500 milliseconds. It's some distribution parameterized by an average and a standard deviation maybe, or some kind of parameter. If you don't know what the distribution is, exponential is a good fallback. You can pretty much gather the data and fit your distribution to it in any kind of statistical tool. But we use exponential as a fallback. Super simple. You can work out what the average is and just go from there. This is the key thing, though. This is the money almost. Source all the data for your plan from real data. Don't just invent it. So Google Analytics, mixed panel metrics. If you've got some kind of metrics tool, please gather that data. If you've got log files, you've pretty much got most of what you need, especially to gather the holding times and the transition probabilities. Any of these tools will give you this data. We have a a tool that we're going to release open source that does this automatically for Google Analytics and generates JMeter plan, and I'll show you what we did for that in a minute. But the point here is unless you're generating this from real data, it's pointless. Now, the question that often comes up at this point is, well, what if I'm building a greenfield system? Well, that's really interesting. One thing you do is just like scroll the internet for people who are similar, and if they've got similar data, like there's loads of public usage stats and so forth about bounce rates and all that kind of stuff, you can build an approximate model. At least assume that there's some kind of drop-off for people who enter the site and they all don't do everything perfectly. Build a model that has at least got wait times, has got users who leave, has got transition probabilities, and then as you gather more data from production, you can refine it. At least try to make your virtual users look like some kind of real user. The other key, and I wish we could spend more time on this, but this is like a day's worth of presentation in itself, is how do you handle performance tests that mutate data? This is quite hard if you don't have a good design for it, but there are two things that work really well. First of all, make sure you invest in being able to snapshot and restore data at the beginning of each test. If you run one load test and it generates a bunch of data, then you run another load test on top of that and another load test on that, you're testing against a moving target. And that makes it harder for you to compare one test results to another. And if what you're trying to do is to detect, has the performance of my system regressed, has it got better, doing that against a moving target is very hard. Snapshot and restore is your friend. If you're working in the cloud, this is probably going to be fairly trivial. You can use some API calls to snapshot your database and so forth. If you're not working in the cloud, backup and restore probably is the simplest option, but it does work, and it is worth the effort, because otherwise the numbers you're getting out are to be called into question. Unless you're a statistical genius and you can control for the variance, which if you can, please come and talk to me, because we'll probably offer you a job, that is going to be your best approach. But then when you're actually generating the data, when you're actually thinking about like going through the test and you've got this virtual user, and it helps to think, in my mind, it helps to think about each execution of your test plan, each thread in JMeter as an actual virtual user, as a real person, or at least a simulacra of a real person. You want to assign that virtual person an actual identity right up front, so that they behave in a certain way right from the beginning. And these kind of mutation workflows sort of change the transition probabilities. It's probably best to look at this in diagram form. So imagine a very naive mutation approach for skipjack.com, where we can go from the home page and you either sign in or you can sign up and then sign in. So there's like one workflow here and there's another workflow here. And I've got one user, rob@skipjack.com, and the fancy password from XKCD. And this is an existing user. So if he chooses this path, he's going to try to sign up. It's not going to work because this is an existing user. It's going to crap out, and then this is going to fail. If he chooses this path, it's going to be fine. What I really want to do is early on discover how many users are new and how many users are existing, and then use that as a transition probability in my model as well. So I've got this like decision thing here. It's a circle in this model, but all we're saying is for everyone who starts, 90% of them are new users and 10% of them are existing users, and they get assigned data differently. So Henry is an existing user and he can go through the sign-in process. Sorry, he's a non-existing user. He can sign up and sign in. I'm an existing user, so I can just sign directly in. This model of having data sets for each kind of user, each kind of workflow, is critical to making it work properly. What you can't just do is start pulling random data out of the air as you work through the test execution, because it won't work. You'll just end up creating a whole ton of data, and complex workflows do not tie together. That's a major issue. JUnit has great features for just injecting massive CSV data sets. So if you've got a load of existing data you want to kind of feed into a test plan, and you want it to go through a process of like signing in and so forth, just export it from your data set as CSV and feed it in. Definitely don't hard code it in the test plan. Feed it in as external data. But assigning each virtual user a real identity makes the design of this so much more simple. I want to emphasize this point as much as I possibly can. Each user is different. And if you don't capture that difference in your model, then you're not testing what your audience really looks like. If you try to make each user look the same, you're not going to get good data. We've seen in our tests huge differences in optimization outcomes based on naive models where we've just assumed that every user is the same, and models where we've actually tried to model what exactly happens in production. The optimization outcomes for the good model is so much better than the naive outcome. And production data is the best source of these parameters, the best source of this model data. So once you've got this plan, you've got to run it. So you've got to build it into some kind of tool, and we'll look at this in JMeter in a second, and then you've got to run it. So step one, high fidelity load test environment. You need something that's going to approximate production when you're doing a load test. It doesn't have to be perfect, but the closer you get it, the more you can port the results across. There will always be some constraints. If you've got some incredibly expensive back-end system that you have to deal with, like we had a flight booking customer, they had a third-party flight booking mainframe system or something. It was just too expensive to load test it. You can do some simulation though, and we'll talk about that. You need to make sure you've got enough capacity to generate your load. The worst thing is to leave a load test running over the weekend, come back on Monday and realize that you ran out of capacity to actually just generate the load, and the system sat at 10% utilization all weekend. That was a wasted weekend. Don't ever do that. Don't also forget to instrument the system you're testing. You want to be able to get data about memory usage, disk usage, CPU usage, network usage, everything when you come back in afterwards. Because if there's a bottleneck or there's a problem and you've just spent 12 hours running a test and you haven't got that data, you're going to spend another 12 hours running that test to get that data. Instrument the test, the system under test. Then implement the model. We'll look at that as well. So I said this already, the closer you are to production, the better. Stubbing is acceptable though, but you must do it well. And to do it well, you need to get a good tool that supports this. And we use Hoverfly, an open source tool from Spectral Labs. Daniel's sat in the front row here if you want to pester him afterwards. We've been working with these guys to make this as close as possible to real in terms of how the system reacts in performance. So they already had great support for recording interaction flows, and you send a request in and a response comes back. But we wanted the stub to behave like a real system. So it takes real pauses, and the pauses are variable, and it craps out in the real way, and all those kind of things. So it does behave like a real system. All open source, all written in Go, so you can dig into it pretty easily. Right, load generators. First thing, everyone, don't run a load test from your laptop. Just don't. You've got Chrome running, if you've got Slack running, you've got no chance. Just don't run load tests from your laptop. It's so easy now to fire up a bunch of machines in Amazon or Google or Azure, forgot the name then, and generate some load from there. Super easy. Less is not more here. You're going to run this for like 12 hours. Maybe not even that. So just fire up a bunch of machines and make sure you've got enough capacity. Over time, you'll learn what the right capacity is, but it's better to over provision the first few times than under provision and have to keep doing it. It also helps, I think, to track metrics from the load generators as well, CPU utilization and so forth, because sometimes you can get these really weird results out of your test and the system doesn't look loaded, but I can't figure out why it couldn't load it anymore. And it's often a bottleneck in the load generator. Just gathering some simple metrics, like 5-minutely CPU averages or something like that, will tell you if you were loading the load generator too much. For the system under test, I'm just going to basically bow down to Brendan Gregg here. If you've not read Systems Performance by Brendan Gregg, it's the absolute Bible on any kind of performance optimization. He's now head of performance at Netflix, was once and previous the Solaris guy. He did dtrace and all that kind of coolness. He has this methodology called usage, saturation, and errors. And the idea is that for every resource you want to track, you track a usage metric, a saturation metric, and an error metric. Shamelessly stolen from his website. This is not my work. He has this great table for these resources and more, what kinds of things you should be tracking to get an accurate picture of how your system is performing. So we're all tracking things like CPU percentage, but it doesn't give you actually a particularly good accurate view of how your system is utilized. You need run queue length and other metrics as well. Brendan's got a ton of blog posts about what these things really mean, what they mean now since there have been some recent changes in the Linux kernel, what this means in conjunction with that. Please read that data because you need to understand what these metrics mean for your system. But you need this data. I just want to, one other thing as well, if you're doing Java, anyone doing Java? Okay. Well, you know, some people could be doing Go. If you're doing Java, it also helps to get Java metrics as well. So for every test that we do for Java, we also gather all the JIT statistics, all the GC statistics, thread statistics. GC is almost always the bottleneck we optimize around at Skipjack. So getting the GC data is really useful, especially with JMeter, because great tool as it is a bit memory hungry. I didn't do that. A bit memory hungry, and you will definitely encounter problems with your load generators if they are thrashing on GC. So it helps to get those metrics as well. We use Telegraph, the open source collector for all these metrics. Any tool will do, but you need to be able to gather the metrics. Right, so let's talk about implementing this model in JMeter now, which I think is kind of the crux of the talk. We saw this model before. I've sort of mutated it a little bit, but essentially we've got 5 pages we're going to go to, some transitions between them, some holding priorities, and then we're going to try and code this up in JMeter. Now, the first thing I should say, I'm going to try to sit on my microphone. The first thing I should say is you won't be able to implement this like using standard JMeter construct straight out of the box. It will require a little bit of coding, but not too much. So I'm gonna I'll do the fancy zoomy thing in a minute. So this is a really basic handcrafted test plan that I wrote for Skipjack that uses just standard JMeter stuff. I'm going to expand it all up and I'll walk to the thing and show you what it does. Okay. So I've got a standard thread group. I've got some parameters, we'll look into those in a minute. Then I've got this Markov chain loop. If you were a mathematician, you might have noticed that those diagrams with the transition probabilities and the holding times are a little bit like continuous time Markov chains. It's a very handy way of modeling this kind of test. Then I've got a timer here called holding time, and that's going to be our pause. Then I've got, for each possible state I can go to, so home, jobs, offices, team, and management, I've got a state there. Then I've got this very fancy named virtual user Markov chain probabilities, which is just some code. And that's where the magic happens. So if we just dig into some of these. I'm going to turn the zoom on. That's the one. Ooh. So cool. So I've just set up 3 properties. Active, true, is the user running. State, what state should they go to next? So they're all going to start in home. Then how long are they going to wait for? This is milliseconds, 100 milliseconds. Cool. Then in the holding time, this is just a Poisson timer. I use Poisson time here. It doesn't really matter what we use for this one. And this is just taking the value of that holding lambda. It's going to pause. Now, first important thing here, there's always a default pause here. So every time the user comes through, they're going to take a random weight, Poisson distribution, 100 milliseconds is the lambda. The reason why we want everyone to wait at the beginning is that we don't get a stampede. It's uncannily possible to stampede your system, let it get so saturated that you can never catch up. We've optimized a few systems for customers that were quite slow. They were doing like massive, bulky transactions. So like 10 transactions per second was a big deal for them. So easy to swamp that system. This will help you prevent that if you just don't let every virtual user hit your system at the same time. Always pause to begin. Then these states are really simple. they're just the actual HTTP sampler things you get in JMeter. This is just a GET request. What the interesting bit though is this code at the end. I'm going to zoom out and zoom in. This is groovy. I'm not a particularly good groovy coder, but this is a simple matrix that basically encodes the diagram you saw before. So this is saying move between the home and the job state with 20% probability, and there's a holding lambda of 6,000 milliseconds, 6 seconds. And all we do is basically run a random selection of what we're going to do next and set the variable next state. This is completely portable. The only thing that will change between tests is this line, what the labels are, and this, what the matrix is. All this down here is just completely standard. So this is on my GitHub. You can take it to your heart's content. But of course, you should be generating all this, and I'm going to show you a generated one. So we have a tool that generates all this because it's so hard to do by hand. I mean, that's 5 states. That matrix is already looking a little bit unwieldy, and it's completely unrealistic. Even our simple site has more states than that. We did a site, it was a simple informational site for a customer, it had 168 different states. And imagine the number of transitions there were between that. You're just not going to get that by hand. You have to generate it. So I have one that we generated here. This is a bit more complicated, but it has a few more states in here. But it has, slightly, one of our other guys wrote some simple code, but it's a similar kind of thing. The tool that generates this just takes all your data from Google Analytics and basically outputs a YAML file. And the YAML file describes every state, every holding parameter, and then you can kind of customize that YAML file. It's much easier to read than this. And there's a command line client to turn it into JMeter. All going to be released open source in the coming weeks. So we're going to be feeding in support for access logs and other data sources, so you'll be able to generate your own JMeter plans from your own production data completely free and open. Easiest way to do it. Once we've got that, we can actually start doing the test. We've got like 15 minutes, so let's discuss that. You might have noticed, and it's all the test plans we generate are parameterized this way, but I parameterize my own by hand. It helps if, when you're running JMeter, first of all, you should always run it from the command line, never from the GUI. The GUI by default stores every single sample in memory to generate like a histogram, which obviously takes unbounded memory, and therefore you spend most time GCing after you've run a few tests for a couple of hours. So you need to run it from the GUI to get decent performance. But what you want to be able to do is use the same plan, but up the concurrency level each run. So the concurrency level is parameterized just as a variable, and you can pass it on the command line. So what I've got here, run with X users, then make X plus some factor or multiply by some factor. You're doing the same plan, but you're injecting parameters from the outside. It helps to spend a little bit of time getting familiar with the JUnit, CLI, the kind of flags you can pass in. But remember, the key thing, you can parameterize basically anything from the command line with JMeter. I keep calling it JUnit. With JMeter, it's so powerful. You can pass in different CSV files of data, different waiting times, different scales for your waiting times. Make sure that when you're building your plan, all the things you need to change, you can change from the command line. It's time consuming and error prone to do it by hand each time. You might run the same test with different concurrence levels 15, 20 times. You don't want to be changing the test file 15, 20 times by hand. So the first thing you need to do early on when you're trying to figure out how to answer all those questions we determined earlier on is figure out where your system is saturated. How do we detect the saturation point? The super low tech way is to check the results by hand. It's so easy to eyeball it. You'll eventually just load your system so much that it'll become apparent that it's saturated. A little bit of binary search in between the points you know are good and bad, and you'll figure out where it is. You can do this by checking a plot rather than checking a table of results. If you want to be high tech, you can fit a curve to that plot, and you can take the derivative of that curve to get absolutely bang on. This is actually surprisingly easy. All the code for this is on my GitHub as well. You can do this in Excel, I think. I did it in R, but it's super easy. This is the model we take for every system. So our load test is completely hands-off. Once we've got the plan, we figure out all this saturation point automatically, and we basically do it by taking measurements, fitting this curve continuously, finding out, where do we think the saturation point is, pushing the system closer to that, refitting the curve, and keep going. So this is some data I got from the Skipjack website. What was the load level? So this is the number of threads or kind of concurrent users. Remember, each of these users has got pause times in there. They do different things. So as they ramp up, they sort of start to look more like real people. It's the number of concurrent users, not the number of actual users. So like 80 concurrent users, I made 30,000 separate requests. So how many users that was, I'm not quite sure, but it's, some users will make one request, some will make 3, some will make 2, who knows. Throughput here was 37 requests per second, and then my error rates. Now, these are useful. If these get massive, you can figure out that something was wrong. You should expect to see some kind of errors, especially if you're running in the cloud. If you've got like ELB or anything like that in the way, you will get random dropped requests and so forth. But even here, like 32 errors on 57,000 requests isn't bad at all. You can do the stats to figure out what those bounds are, but it's easy to eyeball that. Checking a plot is so much easier though. Just plot the data. It's easy to see that we got here, and then all of a sudden things got really bad. And remember what I said before, you won't keep seeing that scaling. You will eventually see some retrograde scaling. It would be unusual to find a system where if you push it long enough, you don't see that retrograde scaling. Be that as you increase the number of concurrent users or you increase the number of machines, eventually you'll see some kind of down peak. And this is what you're looking for here. Maybe here, but these are like pushing your system to the absolute max. A little bit of maths. Anyone recognize this? This is Gunther's Universal Law of Scalability by Neil Gunther. It's actually really simple. Basically, it says the relative capacity for our system, like the true capacity almost, is a function of the number of actual users or the number of actual machines, if you look at it from a different angle, with some contention overhead, things like waiting for the disk, and some crosstalk overhead, things like waiting for locks. And you'll notice that the crosstalk is quadratic in n, and that's where the retrograde scaling comes from. If you take this bit out and you rearrange these terms, you've basically just got Amdahl's law, which gives you the asymptotic bound. But this gives you the real world where things get real and you actually get worse. And this happens not just as you increase the number of users, but also the number of machines, but also the number of processors. So we did a test for a customer, and their system got worse as we went up a generation of AWS machines. And we figured out we'd gone up from 1 physical socket to 2 physical sockets. And the way their system was architected, it couldn't handle the NUMA boundaries, the memory boundaries. There was just too much crosstalk, and the system got slower, not faster. So this algorithm is incredible. This equation is incredibly useful for modeling any kind of scalability. There's even a great research paper that shows that this applies to communication in organizations. This is why massive teams don't work, because the number of communication paths is quadratic in n, and then things just degrade from there. If I fit this curve to my data, this is what I get. It tells me that a more realistic model, because obviously these measurements are just samples, a model of my system's true scalability is roughly that curve. And if I took more measurements, I'd get a more accurate fit and so on and so forth. I'm not looking for the absolute accurate fit. I'm never going to push my system to absolute max saturation. I want something that's a good guess that I can use to set up alerting, to set up capacity planning, to buy more machines. And then I can find the derivative of that curve. And when the derivative goes from positive to negative, which is roughly about this point, we can say that is the absolute saturation point. And I think this is 126 concurrent users for this system. That's about, I think it's about 25, 30 lines of R code to generate all those plots, do the fitting, find the derivative. Super simple. But as you saw before, like, you don't need any of the fancy maths. You can just find it out by doing a graph, and you can do that in Excel, and you can do that by hand, right? It's not hard. If we fit that to here, go back to take that boundary of 120 and 130 concurrent users, we see that actually, yeah, throughput was 52.4 here and 48.3 here, so definitely somewhere in there falls the saturation point. By testing to saturation point, what we've got now is a whole slew of data. And we're going to use that data to dig into the actual latency now. So to analyze these tests, your absolute first step is learn R. That's the one recommendation you should take away from this conference, this Java conference, is to learn R. Don't learn Python. Don't let anyone else tell you to learn Python. R is what the cool kids use. Exploratory analysis, by that I mean just like plotting and looking at tables, will do most of the work for you. There's nothing fancy here. You can do some clever stuff like I did, but you don't need to. Most of your questions are answered just by doing some plots. And let's look at that. So what I did here was I took the load level I think that represented saturation and just plotted the latency. So now when we come to do latency analysis, it makes sense, most sense, to do analysis within a given load level, because obviously latency is different dramatically as load levels increase. So you want to take one load level at a time. And this plot's useless because the system is so fast that the vast majority of things happen so quick. So that didn't really work, but you get a sense already from a basic histogram that there are probably not that many problems with a system like this. But you can take a log scale histogram, and this gives us something really interesting, which is there are actually two peaks. One peak here and one peak here. Can anybody guess what those two peaks might be? Super common in any kind of web system. Cache uncache, absolutely. If you ever see this, you go, oh, what is the problem? Cache uncache, almost always. So these results served from cache, these results not served from cache. These are obviously the outliers. The log scale can really help you. It's nice to facet things as well. So by that I mean split it out by home, jobs, management team, whatever, just to see if there's any pages in particular or any endpoints in particular that are problematic. Again, nothing interesting about this system, it's just a simple website, but you can see like home is a lot faster than some of these. Can't remember why the offices page was so slow, really frustrating. Management, no one's interested in the management team at JAX, so we don't get a lot of samples for that one. It is useful though, if you see this and you want to dig into this, you might need to do a load test where you focus more traffic on this page. If you find you have a particular issue with a page, you need to run the test for longer. Don't just run a test on this page though. Run the whole test for longer until you've got more samples for this page, because all the other things are still happening in the real world. Probably familiar with data like this. A time series is a really nice way of visualizing things. You just see like loads of, so this is the runtime across here, and this is the latency. So these are like each request in time order. You see these spikes and these big spikes. Any guess what the little spikes are? No? Any guess what the big spikes are? GC. Yeah, minor GC, major GC, minor GC, major GC. We had data, I wish I had the plot. I had data of recording the GC time and plot it over. It's like a perfect match. That's why I say take the GC, because if I really wanted to, I mean, this is not very spiky. If I wanted to, I could try and smooth that out. And if we did an optimization, we would smooth that out, but that's fine. And then if you're just doing like reports and stuff, and you're just analyzing for stand-ups and whatever, I find the table to be probably the best of all visualizations. You just take each endpoint and the different percentiles and go from there. And like I say, I generated all of this, literally all the HTML for this, all with a simple R file. You could output everything again and again and again repeatedly. If you're using Jenkins or whatever, you just chuck it on your CI server, it's all there ready for you. Did it per load level as well. This is super interesting because saturation point is never where you'll want to push your system to. You probably have your own quality of service levels for latency. So this helps you understand. So we might say, well, actually, we don't want a 99.9 worse than 1500 milliseconds. So actually, we're not going to push it more than 80 concurrent users. This is a really useful visualization. That typically correlates much more to the kinds of metrics that have an effect on your revenue. Like what's your 95th percentile latency, tells you how much capacity to provision. You can break it out for however long you want. And then I did it by load level and page. The real point here is it makes sense to experiment with as many visualizations as makes sense. Don't just do one plot and assume that's everything. Sometimes there are different scalings, different plots, different tables that help you understand. Definitely analysis by endpoint, analysis by load level are critical, because otherwise you're not getting the full picture. And it also helps to understand the load in the context of your metrics. So if you see regularly 20 concurrent users, and these are your numbers, then you have nothing to worry about. If you regularly see 110 concurrent users, and these are your numbers, you're starting to have something to worry about. You need to be thinking about where's the extra capacity coming from? Is there some optimization we can do? All of this has to be taken into account. It's a continuous cycle of where are we in production? What does the system behave like? How does it scale? Feed that back in. Just to summarize then, load test with a purpose. Don't just run a load test. Don't just throw loads of load at your system and hope some insight comes out of the back. It's not a pass-fail test. It's something you do with meaning. Real user models, please. No page 1, page 2, page 3, page 4, page 5. Start again, page 1, page 2, page 3, page 4, page 5. Don't do that. Real models. If you're in production, you've got so much data, you can build a really good model. That load curve exploration is critical. It's going to give you all the answers you want. It's going to tell you about how your system behaves with your current load, where your saturation point is, what's the quality of service going to be in between those points, are you over-provisioned, under-provisioned? You can answer all those questions. Obviously, the real data matters, both in terms of what you put into the model, but also how you interpret the numbers. Like I said before, if you can handle 120 users and you've got 10 at the moment, you're fine. If you've got 110, you need to rethink problems. But everything, if you remember anything, performance matters. 300 milliseconds, £8 million. That's a lot of money. Thank you very much.